So, AUT 208. This is troubleshooting or system diagnosis and troubleshooting is what it's referred to. Uh, so what we'll do is we'll come back and try to review some topics that some of y'all might have already known. Some of y'all probably might have had these classes, but the only real prerequisite we have for this course, originally what we was going to do is we were going to teach this as a capstone course or at the very end of the program. Things didn't work out, and we actually stuck this in pretty early. And then we realized doing a system level troubleshooting, we don't have to have a really understanding on how things work. What we need to do is just understand what they do. And once we realize that, we realize that as long as we have basic electrical theory, then we should be able to take this course. So it really helped us as far as scheduling. So these are some of the topics we're going to look at. We're going to look at electrical, which is hopefully a review for some of y'all, and we'll add some more about electronics, which some of y'all might have had solid state, some of y'all hadn't. But like I said, we're not going to learn exactly how these electronic devices work, how they work, and do all the math that we normally do, that I love, but some of y'all don't. But we're just going to look at it from, okay, this is what it does and how it does. We're not going to be concerned with. And if it don't do what it's supposed to do, then we replace it. Like I said last class, we very seldom do component level troubleshooting anymore because the cost of technicians is so much, and I could sit down at a workbench and take 2 or 3 hours to fix something. Well, they could have bought that thing a couple of times over by the time they have to pay me to do component level troubleshooting on it. So a lot of our, especially a lot of our sensors, these guys they're not designed, they're sealed because they're designed to run in very harsh environments. So now they actually seal them up. I've got one, I need to go find it, and you can see there's no way in the world you could take the thing apart and fix it even if you knew all the schematics and everything how to work. So we'll start off with electrical, and most of y'all have had this because DC is the prerequisite for the class. And I think some of y'all has even had solid state, and some of y'all has even had digital already. So basically, the components. First of all, we need to understand that we got two different power sources. We got DC, which stands for direct current. This is electrical current that only flows in one direction. This is what you learn in DC, and you learned about voltage, current, resistance, and power. So you learn these laws. You learn, Ohm's law. You learn Watt's law, and you learn Kirchhoff's law, which basically varies. We have one law that deals with series circuits, and we have one law that deals with parallel circuits. AC, this is voltage or current, resistance. We got basically the same thing. We got power, but in AC we have voltage, current, we have resistance, and then we have something called reactance, impedance. And we have two types of power in AC. We have what we call true power and apparent power. So anybody that tells you that AC and DC are the same has no idea what they're talking about. They are not the same. AC, we can do things with AC that we can't with DC. One thing we can do is we can induce a voltage with AC, which we can't with DC. And when we take a break, I'll go over here and get my little unit over here that shows you how I can turn on an LED and not actually have a circuit between the two because it's induced. So we have induction motors that only work off AC. And then, of course, we have transformers, which allows us to step the voltage up and down. And also it affects the current that most people don't understand. And I don't know if we'll get into that or not. Conductors, of course, we know that conductors are usually made out of metals. Probably the most widely used conductor, and that's probably a toss-up, is copper or some type of copper alloy. We have a big problem with copper in that it oxidizes, which means it rusts. And everybody's seen copper that rusts. If if you've seen the Statue of Liberty, you've seen copper that's oxidized or rust, and that green coating that's on the Statue of Liberty. A lot of people don't know the skin of the Statue of Liberty is actually copper, and of course it's out there in the ocean or in the bay, and it basically, the salt water has actually turned it green. Uh, Copper alloy is just copper that's either been coated with a thin coating of tin or actually an alloy, and basically the only reason they do that is to prevent it from oxidizing or rusting. Aluminum is a fairly good conductor. We use it for our high voltage lines and low current high voltage because it has some resistance. We have stranded conductors, solid strand conductors, and then we have fiber optics, which most of y'all under or have a basic feeling about fiber optics. This is when we send information through a fiber optic cable with light, which basically so it does move at the speed of light. Current moves almost at the speed of light, but fiber moves at the speed of light. But the advantage we have is we don't have to worry about this guys right here. We don't have to worry about reactance. We don't have to worry about impedance, which we run into in AC. And of course, the information we're sending you is constantly changing. Plus, we don't have to worry about electromagnetic interference that we get from any conductor or anything carrying AC. So there's a lot of advantages of fiber that gives it the ability to operate at extremely high speeds. So over what we try to do with switching information over a line. Control devices, we'll look at switches, push buttons, contacts, and also sensors. We'll also touch a little bit on PLC, programmable logic controllers, not from a programming point of view, but from a wiring point of view, from the outside. Of course, if you wanted to learn how to program logic controllers, programmable means we can put our own programs in them. So when we come in and we look at the Amatrol line, these are the PLCs down here. I think I showed y'all last class. So these are the programmable controllers right here, and they look identical to each other. So what makes them different, of course, is the programs that they're running. So this is a big advantage of that, is that, if we got a PLC that fails, we don't have to have a PLC for every module or of a manufacturing line. We can just bring in a new PLC, wire it up, and these PLCs now are made to wire real fast. In the old days, they weren't. But now, and then swap it out, put the right program in there, and then we're up and running. And so these are the PLCs. So these are Siemens 314s and we'll talk a little bit about those. And also they help us troubleshoot with all these lights that's going on right here. So you can see this light right here is blinking, and you look up here and you see this is blinking. Well, this is controlling that. So if I come over and see this blinking, and then this right here is blinking, then not blinking, then odds are we've got a bad connection between the output of the PLC and the device itself. So PLCs also help us in troubleshooting a lot by being just by reading the lights, the status of the lights on the front of these things. Loads. This is what we connect to the PLC. We'll look at resistive, capacitive, inductives, indicators. We'll talk a little bit about motors in this class, solenoids, relays, control relays, contactors, motor starters, and we'll look at those. And the relays in DC. By the way, we will start meeting on campus next Tuesday. Next Monday. I keep getting my two classes confused, so y'all need to kind of correct me. So next Monday we will meet on class, and we will do one lab. The first lab we'll do will be our lockout tagout lab. So y'all need to make sure you review those slides that give you the actual procedures, because that's basically what you're going to be graded on, is following the correct procedures to do lockout tagout. So, of course, hopefully y'all understand Ohm's law, Watt's law, which basically talks about the power in a circuit. Power is work. So, when you pay your power bill every month, you're not paying for current, you're not paying for voltage, you're paying for work. The work is provided by a power company. They're not trying to sell you volts, they're not trying to sell you amps, they're trying to sell you work. Of course, we looked at Kirchhoff's voltage law, which basically deals with series circuits, and you looked at Kirchhoff's current law, which deals with parallel circuits. And then these circuits can be hooked up in series, parallel, or series parallel. And of course, one of the big things that you had in DC was color codes. Now, as you move through your training, you'll see that these same color codes are used by other devices besides for resistors. So they're used for inductors and they're used for capacitors. I've seen them used on diodes. But the color code is the same. So learning those color codes and those numbers that go along with each color would really, really be important as far as, when you move through your career on these different devices. Knowing that color code is very, very impressive. We used to have a competition. They were a for-profit trade school. They would call themselves RETs, and they had their students buy these little color wheels where they could spin the colors into the 4 little slots on the inside, and then read the resistance up there. So we had an employer call in here about a job, and that's one thing he's brought up. He says, don't send anybody that has to use a color wheel to know the color code. So we thought that was so. Of course, Rets is out of business now, I guess, because they didn't teach the color code. They taught the little wheel. And also AT&T, they went out of business too because of problems like that. So in electronics, so y'all should already know this. Y'all should have a really good understanding of Ohm's law and know the formulas in your head. You might even in DC, and you'll use Ohm's law in AC if you hadn't had it already. You use Watt's law, but you'll learn how to apply Watt's law to AC. Kirchhoff's law is the same. So basically what you do is you take the same thing that you learned in DC, but then apply it to an AC circuit. And these devices called capacitors and inductors, they are a lot different. So hopefully everybody's okay with these. Like I said, Ohm's law would be something that you just need to know. Watt's law also, the 3 forms of Watt's law, the way we calculate work. How much work do we get? So watts is work. Voltage, we know we can't get work without force and speed. That's every formula that you'll see about work. Every formula you see about work deals with force and either distance. So that's the way we calculate other types of work or physical work. Then of course in electronics we use force times speed. Of course, speed and distance are directly proportional. So if you cover the same amount of distance in the same amount of time, you have to be going faster. So that's why we deal with those. So if you ever looked at, and we'll look at that when we get into mechanical work and those other kind of things, we'll come back and use this law of physics for work, and you'll see it's basically Watt's law, but we'll use force and speed or this divided by that, but it's basically the same stuff. In electronics, we have devices called diodes, and you've got diodes you might not have known it, but you've got diodes all over the place in your house. So one of the things, direct current, the biggest advantage of DC is we can electronically control it. So that means every electronic device you have operates off of DC. But the problem is, what we have with AC is we can do what we call induction. So we have these things called transformers, which can step the voltage up, or it can step the voltage down. Now what it don't change is it does not change power. It does a little bit because there's no such thing as anything that's 100% efficient. So it means the work you get in is not going to be it will never equal to the work you get out, no matter what system you go through. You always have a loss inside the system. But so the power we put into, let's say, a transformer. So if it was 100% efficient, if I put 100 watts in, then over here on this side, we call the secondary, we would get 100 watts out. Of course, that's not exactly true, but it's good for us teaching. Actually, we might be putting 110 watts in to get 100 watts out because the transformers are not 100% efficient. So what happens is, this is the concept that a lot of people don't understand, is that everything has resistance. So a wire has resistance. A conductor has resistance. And voltage drop, you learn in DC, voltage drop is equal to I times R. So if I try to put current through a conductor, the conductor will drop some voltage. Now, what determines the resistance of a conductor? Anybody know? I'm listening. Now, temperature, I'm going to put that down here on number 4, because that's down, yeah, temp down here, so that's good. Yeah, the size or the gauge, yeah. Of course. What's that? That doesn't return, current, that would be like saying that the size of a resistor is determined by a current. So you're saying a 100 ohm resistor, that 100 ohms is determined by current. Is it determined by voltage? No, it's not. It's determined by its size. It's determined by its material. Well, this is wires. This is wires. What we're trying to do is determine the resistance of the wire. It's the size. It's the material. Length. So this is the 4 things that determine the resistance of a wire. It's how big it is, what material it's made of, how far you run it. So if you ever looked at an ampacity chart, it's rated in ohms per 1,000 feet or ohms per meter or something like that, or ohms per kilometer. So length, and then the temperature. Metals, when we heat metals, their resistance goes up. So what that means is, if I've got a wire and I'm trying to send 1,000 amps through it, and it's got 1 ohm resistance, then it would drop 1,000 volts. So this is why you have to make sure that the cables, the conductors on your battery are really good. You keep them real clean, because we only got about 12 volts to work with, and your motor wants 50. Your motor wants 50 amps. Your starter wants 50 amps to turn that big engine over. 50 amps, 1 ohm, it would drop 50 volts. Well, we only got 12 volts. So 1 ohm means your starter wouldn't turn over. So that's why we have to do that. So just very, very small resistance can drop a lot of voltage over distance, and that's why your battery cables have to be really, really good, and you keep those connections up there on the battery real good. And I had a one of my sister-in-laws, her starter wouldn't work. It'd work every once in a while, and the battery connections was fine, but she had a loose connection on her starter. So just that 1 ohm or so resistance on that loose connection, it wasn't her battery, so it was her connection on her starter was actually bad. So what we're saying is though is if I got V is equal to I times R, and then power is equal to V times I, well, I would be equal to P over V. So if I'm trying to send you power, the higher I make that voltage, the less current is going to be required to provide you with that power. So if this is a step-down transformer, which means if I got 100 volts over here and 50 volts over there, if I've got 1 milliamp over here, then I'm going to have 2 milliamps over here. So when we say a transformer steps up and steps down, if we step the voltage down in the transformer, the current's got to go up on the low side to provide that same power. So if you're thinking about, okay, in DC we learned if voltage goes up, current goes up, but that's applying to the load. What I'm talking about is trying to get the power to your load. So this is the source. So that means if I can step my voltage up to 750,000 volts, I could send 750,000 watts of power with 1 amp of current. Now the problem is if I tried to run 750,000 volts into my house, it would arc all over the place. And I don't know if y'all seen the movie Eagle Eye, where the high power line falls down on that guy and he evaporates. Well, that would probably be what would be going on here. So what we do is the power company runs it through step-up transformers to transmit it, and then they start stepping it down the closer they get to you for safety. But you would notice the gauge of the wires get bigger as the voltage, because we're dealing with the resistance. So yeah, but it allows the power company to use aluminum, even though aluminum is a good conductor. It's not the best conductor. It allows them to use aluminum on these really high voltage lines, and it also allows them to use smaller gauges. Aluminum is lighter, aluminum is cheaper. So all your high voltage lines are going to be aluminum. And then your low voltage lines are going to start moving toward copper. So that's the reason, that's the big advantage of AC. And also it induces, so we literally induce a voltage from here into here. So that means motors run off of the repulsion and retraction, repulsion and attraction of magnetic fields. But if I can induce one of them, then that means it's going to, so we have what we call induction motors, where the magnetic field in the rotor is induced in there. So the big advantage of AC motors is they're cheaper per horsepower than DC motors. The biggest advantage and we can step AC up and step AC down for transmission and step it down for safety. For us, down for safety for us. But the biggest advantage of DC is that we can electronically control it. So what we have to do is your power company generates AC, but your TV works off of DC. Your cell phone works off of DC. So what you have to do is you have these things called power supplies that can, in your alternator. Your car operates off of DC, but we run an AC generator out there. So what we have is these devices called diodes. Most of the time in cars they'll call them rectifiers, and that's what they do. They primarily take AC and convert it to DC. We have transistors. These are our electronically controlled switches. So we have uses a small base current to control a proportionally large collector current, and that's not very important. What we need to know is when we get into sensors, they're going to talk about NPN sensor and PNP sensors. And we'll look at that and see what they mean when we get into program controllers. Then we have what we call FETs. These are field effect transistors. These are, by the way, transistors are current valves. Everybody knows how a valve works, right? Well, these are current valves, and we can use them as switches, so we can cut them on or cut them off, just like you go out to the water fountain and you press that valve. That would be digital, or we can control them analog, like the valve on your sink at the house, where we can precisely control the water flow all the way from a stop all the way up to wide open. And if you turn that thing wide open and you tried to hold that current back with that water flow with your hand, you'd be soaking wet because you cannot do it. So what you do is you get a mechanical advantage from the control, the valve control, and the water itself. So that's what we do with these devices. So on a bipolar junction transistor, we use this guy right here to control the size of the valve. On FETs, we use this guy right here to control the size of the valve. The biggest advantage of FETs is they can't handle a lot of power. They can't handle real high voltage, but they work really well in digital, or because we can switch them on and switch them off faster than we can bipolar transistors. But we'll run into both of these. So most of your sensors will use a lot of FETs, but when you get into actually having to provide or control a lot of current, it'll probably use a BJT. So when we get into sensors, these two guys right here are going to come up again, and we'll talk about those. Insulated gate BJTs we're not going to look at, and then ICs. Integrated circuits are when we take an entire circuit and we put it on a piece of silicone. So what happens is that this reduces the size of everything. Means we can't handle a lot of power, but we can make a lot of decisions. So if you ever took your cell phone apart by accident, I went swimming. I had an iPhone 3, and it was in the pocket on my swimsuit, and I went swimming on it, and I decided to try to take it apart and dry it out. But when I took it apart, I realized it was burnt up because I let it get wet. But there was a lot of these integrated circuits in there. If you could take your tablet apart, if you could take your computer apart, you'd see it's got a lot of integrated circuits in there. So some of our sensors actually have integrated circuits, and of course inside the actual PLC itself, there's a lot of integrated circuits. We refer to these as ICs, and basically what they do, we're not dealing with a lot of power. All we're trying to do is do logic, do decision makings. Is it true or is it false? So these devices can be integrated into real small aspects. Some of the Intel chips, and this is another advantage of these guys right here. We can make them a lot smaller than these guys right here. So they're basically made out of a bunch of FETs, and they're up to, good gracious, 1 billion transistors on a single wafer, which is very interesting on some of your processors. So first of all, we got to realize that we have a power supply, and when we use the power supply, these are the devices that convert AC into DC. So we do this different ways, and this DC is usually what we call regulated. So regulated means it tries to maintain a constant output even though you vary the loads. So you see, if you got a cruise control on your car, you got a pretty good idea of what regulation is. So what happens is you get up to a certain speed and you engage your cruise control, and then if your car tries to slow down, the cruise control automatically adds more gas. If it tries to speed up, it takes gas away. So that's regulation. It does a pretty good job, but not perfect. So regulators are going to try to maintain a constant output. Electronic devices like these transistors, they like a set voltage level. So our PLCs our PLCs that we're using is going to operate off 24 volts DC, but that's going to be within like plus or minus maybe 5%, if better. So that's saying this guy between full load, whatever the load is, and minimum load, the output would only vary about 5%. So these are regulated power supplies. We have two categories. We have what we call a linear power supply. These are usually bulkier because the transformers have to be bigger. And of course, the control devices have to be bigger. The big advantage of a linear power supply is they're easy to design. I've built several of these, and they're easy to troubleshoot. So the trainers that you're using have linear power supplies in them. So if you got one of your power supply that goes out, and what's nice about our trainer, it's got those 3 LEDs down there that basically tells you if the power supply is good or bad. So if you got one if you get a trainer that one of those LEDs are flashing at you, or one of the LEDs is out, don't go put it up and get another trainer. I had this happen to me before, where I taught a class, and there was like, there's 5 or 6 trainers in there, and they say, well, none of those trainers work. Because what was happening is the students would go up there and get one, it wouldn't work. They'd go up there and put that one back in, and then they would get the old one out. I worked on a job at a scale company, and some of y'all probably heard that, where that's the way they fix things. So if this electronic scale wouldn't work, indicator, they would swap parts until it started working. And they would take a part out, and if it didn't fix it, they would take the one they put out and put it in their spare parts. So they didn't realize that electronics, a lot of things, more than one thing goes bad. So they ended up with a ton of spare parts in their spare part locker. So it was pretty funny. So if you get out there and you take one of our classes and one of these trainers don't work, don't go back up there and put it back up and get you another one. Give them to whoever instructor is teaching your class. And what they'll do is they'll provide it with me. If I've got a work-study student, I think James has been a work-study student, we'll let the work-study student fix it, and they'll get a really good understanding of troubleshooting these things. If there's not, then I'll fix them. We got all the parts we need to keep these trainers up. Then we got these switching power supplies. These switching power supplies, they're more efficient. They're a lot smaller because they operate at a lot higher frequency. Which doesn't mean anything for you, but look over here, this is 60 hertz. Over here, this is 15 to 50 kilohertz. Well, what happens is our filters can be smaller, our transformers can be smaller, they get more efficient, which means now all of a sudden these devices get smaller. So your computer power supply is a switching power supply. Your little brick or little cube that you use to charge your cell phones and your tablets, those are switching power supplies. But the problem is once they go bad, they're almost impossible to fix. So they're real hard to design, and they're almost impossible to fix. So most of these little switching power supplies, they seal them up. So you can't even, especially if y'all have ever had a computer power supply that goes bad and try to take it apart. And normally it's all epoxied in there. That's one reason they're so heavy. But I've got like an 8-amp a linear power supply that I built, and it's a big old thing. The power supply for this computer plus the voltage. So on these power supplies, they're pretty much well set to run on a certain voltage. My computer power supply, if I can bring my camera over here. Since it's a switching power supply and it converts it to DC to start off with, then these guys are designed to run on a wide voltage and current range. If y'all can read that. So this is this guy his output is 20 volts at 4.5 amps, but it'll operate anywhere from 100 volts to 200 volts, 240 volts AC. So when we went over to Germany, all we had to do was buy the adapter that adapts us from the U.S. Plugs over to the German plugs, which are weird. They're round-looking things, and we had no problem. So charging our computers, we had no problem because of the wide range of this switching power supply. If this was a linear power supply, there's no way in the world, if y'all can see that, I don't think you can, that it can do that. So 20 volts at 4.5 amps, and that's the size of it, but it's all sealed up, which means, and it's epoxied. So if I took this thing apart, there's no way in the world I could fix it anyway. So the advantage of switching power supplies is they're more efficient than linear power supplies, but they're almost impossible to fix, and they're hard to troubleshoot, guys. I've tried to troubleshoot them, and this feedback loop right here, everybody's set up to cause it to oscillate, but it don't oscillate, so we got big problems. But these guys are starting to dominate it because we're starting to do, most of this time when these power supplies go out, we just replace them. These guys, though, we fix them. So all our trainers use these power supplies right here. So this is the setup of a basic control system. So this would be whether it's relay logic or whatever, but this is the basic way we do. So first of all, every control system has inputs that we're going to connect into the control logic. These could be switches, these could be contacts, they could be sensors, a lot of different things that come in here. Then we take the inputs and then we run it into a control logic. This could be relay logic, which you'll learn about relay logic when you take PLCs, and you'll also learn about relay logic if you take motor controls. I can't remember if motor controls is a required course in the AUT or it's an elective course, but it's a really good course to take. Could be a programmable logic controller, which is what we're using. Basically, it's a combination. Most control systems are a combination of relay logic and PLCs. Programmable logic controllers are nice, but they can't handle high voltages on their outputs, and they can't handle high currents. So what we usually do is we'll let the PLC run a relay, and then the relay can do what we need it to do. PIDs, these are closed loop systems, like temperature controls and stuff like that. And we'll look a little bit at that. Could be a computer. So when I first got the first computer controlled, now PLCs are computers, but these are designed to be industrial grade, and they program in languages that people that came up through the trades can handle. These computers, these guys right here, these are full-blown computers. This is where they take a computer, a regular computer, and then they use some of the ports to actually control different devices. So when the first one I saw was when they put in number 8 blast furnace out at U.S. Steel, which they're not making iron anymore. And it was controlled by two big digital corporation computers. It was two. One of them was online, and the other one was mirroring it, and it was a standby because melted iron kills people. So if one of the computers fail, then it automatically switch over. The shuttle had 5 computers on it. It had 4, and then the 5th computer was the guy that made the final decision. If we had 2 computers that was running the flight controls, if they disagree with each other, then the 5th computer was designed to figure out which one had the most likelihood of being correct. What they're doing on these space capsules now, I'm not really sure, but I was pretty familiar with the space shuttle. Anyway, and microcontrollers, these are small little PLCs. One of the ones that I've dealt with is called the Arduino. We can get this. It's got several input ports on it, output ports. It's a really neat little, but it programs in a text-based language, very similar to like Pascal. So it's hard to program. These guys right here are going to program in logic. When you take motor controls, the main programming language in this is what we call ladder logic. And if you're going to work in industry, then of course in the ILT program, motor controls is required. I think in the AUT program, I think motor controls is an optional class, but guys, that would be one of them that you would consider. In the ILT program, you would consider taking extra PLC classes at some of your electives. In your AUT program, you would make sure you do PLCs, but PLCs is required in the core, and then there's 2 other PLC classes that you could take. Microcontrollers, we don't teach those. We do teach relay logic. We do teach PLCs. Like I said, PLCs are so important in industry right now. We have actually three levels of PLCs. We have Introduction to PLCs, which is ILT 194. We have Advanced PLCs, which is ILT 196. It has an NC3 certification in Allen Bradley PLCs. And then we have ILT 212, which is called PLCs and Automated Systems. Here we will actually, in that course, we'll actually take one of our manufacturing lines and convert it from Allen Bradley PLCs over to Siemens PLCs, and there'll be a certification in Siemens PLCs in that course. We don't have it in Intro to PLCs, of course, because that's an introduction class. So. But Arduino, you can get this Arduino microcontroller for like 26 bucks. And it's really, really neat. It's just hard to program. It takes a lot of knowledge to program it. And then sooner or later, we're going to make a decision to generate outputs. This is where your relay coils are going to be. This is on computers. This would be your display screens. This would be your thumb drives and stuff like that. So a perfect example is your cell phone. So you got inputs on your cell phone. You got an on-off switch. You got volume controls. And then you got a touch screen on there. And then you got outputs. You got a speaker that plays at you. You got a microphone. Well, a microphone would be an input. You got speakers, and you got your display, that's in beside. So you're not actually touching your display. You're touching a coating on your display that allows you to touch it with your fingers. I mean, it's part of the display, but it's actually 2 units. So the touch screen is actually a membrane across the top that is basically a capacitive sensor, and we'll look at that when we get into those. So this is the basic makeup of a control system. And okay. So control devices. First of all, in this class, let's see what time it is. Okay, we'll do about. So let's go ahead and let's do a 10-minute break, and we'll come back at 6:30. Okay, 10 minutes. So in this class, we're looking at it from a PLC, and this is when you buy sensors. The problem is that y'all know in DC that we have to have a circuit. So in ladder diagrams, we do our 2 power rails like the rails, the outside rails on a ladder. And then what we do is we come in and we hook up we draw our circuits in between. So what we have is our PLC has an input port where we're going to hook up things, and we'll show you that when we get there. And then we come into the PLC itself. And then the PLC itself, its circuits would be connected over here. So this would actually be the input. So I would come over here and I would take like a push button and hook it right here. It comes in. Well, in PLCs, they're different. So I could make this a positive, and I could make this a negative. So what we're saying, so right now, if I came over here and hooked up a bunch of input devices, and I'm just going to put push buttons, but these could be actually sensors, then we call it, so this would be a common. So don't get, a common is just a conductor that a lot of devices hook up to. So right here, these push buttons are using a positive common. So if the push button uses a positive common, then the PLC's got to use a negative common. But I could have just as well have came up here and did this. So I could have came up here and I could come over here and make this minus and make this plus. So over here, my input devices are using a negative common and my PLC is using a positive common. So, and this is what, and it comes into play when you're buying the sensors. So this is something you have to know about your PLCs. So all these PLCs over here, are using a negative common. So that means this over here has to be a positive. So if it uses a positive common, we call this sourcing in PLCs. And a negative common, we refer to that as syncing. Now in digital, you'll learn how it got those names, by the way, because of the way the outputs of a digital gate works. So all our input devices on all the PLCs on the Amatro line are sourcing. So that means the PLCs have to be syncing. We run into the same thing on our outputs. So on our outputs, if our PLCs are sourcing outputs, so that means they're using a positive common on the outputs, and it's running. So that means the output devices have to be syncing. Well, on sensors, when you buy, if you buy a sourcing sensor and hook it up to a sourcing input, nothing's going to work. So you go out and you got a bad sensor and you buy the wrong type sensor, you hook it up, it don't work, and you say, okay, we got a bad part. Well, the problem is you bought the wrong part, right? You understand? So so you need, first of all, you need to know what the common of your PLC is. So no matter what the common, if your inputs use a negative common, then you got to buy sourcing sensors. Does that make sense? Because negative commons on your inputs means the devices, the sensors have to provide the plus. So sourcing sensors are called PNP sensors, and syncing sensors are called NPN sensors. So a PNP sensor means that the PLC has a negative common on the inputs, and then a sourcing. Did I say that right? So let me get this. So this is what we're using right here. So our PLC runs a negative common on the inputs, which means we better buy what? We better replace our sensors with PNP sensors. So that's what, but the manufacturers don't say they're syncing or sourcing. They say it's a PNP sensor or an NPN sensor, and it's up to you as the technician to know which one. So this would get you into trouble, right? You know, because you'd be, well, let's order another one. You turn around and order another PNP sensor. Hook it up, it don't work. So you say, oh, well, heck, the PLC must be bad. So you replace the PLC. Redo all the programs, redo all the wiring, hook it back up, and the sensor still don't work. And the problem is your problem is that you replaced it with the wrong type sensor. So over here in the U.S., it's popular to run syncing inputs, which means you need to buy PNP sensors. And the outputs are over here in the U.S. are usually sourcing outputs. So that means they output the plus, and you need to connect the minus to your output devices. We don't really worry about that as far as lights goes. Light indicators don't care about polarity. Relay coils don't care about polarity. So a lot of our output devices don't care about polarity, but I'm guaranteeing you sooner or later you're going to do that. So you need to know on your PLC how the inputs, and you can some PLCs allow you to change them up. So when I look at this PLC right here, let me bring my camera back up. By the way, this is the PLC that you'll use in Intro to PLCs, which is 104. So these are the inputs up here. So this is where we'd hook our sensors. And we'll look at this addressing before long. And this is labeled DC common, and that's labeled DC common. We have the negative hooked up here. So I've got the negative DC supply. The positive DC supply has a red line on it right here. If y'all can see this red line right here. So this is actually coming from the power supply on the trainer. It does have an internal power supply, by the way. So this PLC powers up off of AC. Well, some PLCs power. So this guy's got an internal power supply on it. It's just that this power supply is not designed to run a lot of current. It could run switches and push buttons, but it couldn't run like an inductive sensor or any of the solid state or electronic sensors that we'll look at. So what we're doing is we're using the power supply inside this guy. So this has got a nice DC power supply in it, and then they run the power up through here. So the red wire, this is plus 24 volts, and this over here you'd have to just look at the wiring diagram. So what we have is we have the negative running here to this common, and then the negative running here to this common. So we have our PLC is set up to sync. What's nice, but you can't do each individual input, but you can do them in groups. So I could set this up to source and set this up to sync on this PLC. Most PLCs this is built into the PLC. You get that when you buy it. So you'll buy syncing input. You'll buy a PLC with syncing inputs. And like I said over here at the U.S., I'm not going to say you're going to run into that all over the place. Predominantly in the U.S., we run syncing input ports, and we run sourcing output ports. So if you look real close, you can see all these commons down here. So we can actually set. And what I've done is here's the plus, and I've jumped the plus to all the ports. So we have this PLC set up for sourcing outputs and syncing inputs. So if the inputs are syncing, that means my sensors have to use a positive common. These over here, these are sourcing outputs, so my output devices have to use a negative common. So that's very, very important to know. Like I said, most of your output devices are not polarity sensitive, but these solid state sensors that we're going to look at, these electronic sensors are. And every company that I know of makes the same sensor as either NPN or PNP. So, so you don't necessarily have to get the sensor. If you know the sensor and you know what it does and you know the type, you don't necessarily have to get it from the same company of the one that you're replacing, which is pretty cool if you just know that money. So the company to replace it might want $50. You might find it somewhere else for $25, and you make your boss happy. So syncing sensors, these are called NPN sensors, and sourcing sensors are called PNP. The input device of the PLC input has to be opposite. So sourcing sensors have to connect to a syncing input and vice versa. Everybody okay? An output device and PLC output ports has to be opposite. So if I'm running a sourcing output, then all my output devices have to use a negative common. So that's really important to go when you wire up these PLCs. So these PLCs are programmable logic controllers. So we bring inputs into them, then we run through a program that was written by somebody, and that's You'll learn that in the Intro to PLCs. I think that's in both the ILT and the AUT. I think it's up in the core, because that's the name of the game. In manufacturing, PLCs are the name of the game. I mean, and the more you know about them, the more you're going to be in demand, getting out of here. And anybody that's working in the industry right now. Broza wants their techs that's going through their intern program to take all 3 PLC classes, because they understand, the benefit of these employees knowing as much about these programmable controllers as they possibly can. They want them to take a lot of robotics classes too. So these are some input devices. These are push buttons, very simple devices. Normally, industrial grade push buttons are big, because most of the time they need to be operated. A lot of places you go to, the employees have to wear has to wear gloves. So even our HMI panels, our human machine interface, by the way, which is a lot of things, but over time, these graphic panels that we hook up to a PLC. So this one is not programmed, but you can see it over there. So this is an HMI panel. This is put out by Siemens. This one is not programmed. The one over here, this guy on the Festo line, this is programmed to run this section. But these don't use the same type of screen that you have on your computer. So you could go up there all day and just touch that lightly. It wouldn't do anything. This actually requires you to put pressure on it. It's a resistive display. So you can operate these even with gloves on. So I don't know if y'all have ever in the wintertime tried to use your phone and you end up taking your gloves off, unless you buy those foams, those gloves that have those capacitive tips on them, which allows you to do that. Or if you buy a pen that's got that on there that you can use. But these guys right here, they're actually use what we call resistive panels. So you literally push in on them and you actually change the resistance on where you're touching. But you have to push on these. Anybody that's ever used these, you can't just touch them like you use your phone. You literally gotta push in on them. But so what they do is these push buttons are usually big enough to be operated with people that's wearing gloves. So we don't see any small things out there. We see large things, push buttons. So these are pretty common. Selector switches. These are selector switches. They're pretty good size. These would be where you can select more than one option. These are e-stop buttons. These have a big mushroom head on them. Very easy to hit. You don't have to think about them. So here's the big old e-stop buttons on our manufacturing line. Oops, that ain't gonna do no good. That's right. So here's the big e-stop buttons right here, and these are pretty cool. When you hit e-stop, it drops out this relay, by the way. So e-stop buttons have to be hardwired. They can't be programmed. They got to be hardwired, because programs can crash. I know every once in a while your phone screws up. You go over there and you tap on the front, nothing happens, and you turn your phone off or do a reset on it, or you exit the application and you bring it back up. If it works, that's okay on a cell phone. That's not life and death. So all these are actually relays. They usually have a safety relay in here. So what happens is once we energize this thing, we hit that, it kills this. And by the way, this is pretty neat. These are all, right now they're disconnected, but they're all wired together through a network. And if you hit this e-stop right here, it kills the e-stop relay on all the modules, which is pretty neat, which is common too. So these are selector switches or push buttons. These don't have a polarity, so there's no such thing as syncing or sourcing push buttons. So this doesn't make any differences when you get into your solid state sensors, where this is going to actually come into play. So sensors. So what does a sensor do? Well, a sensor, electrical sensor, does exactly what your senses do. So your sensors basically. your brain processes two types of information. It processes chemical and also electrical. The electrical is the predominant. Your chemical sensors are your fear. When you get scared and stuff like that, that would be chemical in your brain where it's at. So most of our sensors are electrical. So what a sensor does, or what your sensor does, it takes some type of physical stimulus and converts it over to an electrical signal, and this electrical signal is sent into your brain where it processes. So your brain cannot smell, your brain cannot touch, your brain cannot see. Your brain is just processing electrical information that's been converted from a physical stimulus over to an electrical signal, and that's what your brain processes. So this is exactly what these sensors that we have does. It takes a physical stimulus and converts it over to an electrical signal, and then we process that with our controller. So we have sensors that sense presence. We call these, by the way, presence. These would be what we call non-contact. So I should put that over. So these sensors sense presence without physically touching the device it needs to see if it's present or not. We have sensors that sense length or size or distance. We have sensors that sense position. We'll look at those. We have sensors that sense pressure. We have this on both our manufacturing lines. We have sensors that sense flow. We don't have those on our manufacturing line, but you'll run into those where these fluids or flow of the fluids is critical. We have sensors that sense light. We'll look at those. We have sensors that sense sound. Our manufacturing line does not use this, but on your phone, you got a sensor that senses sound. We have sensors that sense temperature. This is not on our manufacturing line, but they're on manufacturing lines out there. We can sense speed. We do have those. Sense weight or force. We don't have any of those on our manufacturing lines. And of course, human-machine interfaces. But technically, a push button is a human-machine interface. But normally when we talk about these HMIs, we call them HMI panels. These are these touch panels that are becoming so popular because they're graphic in nature. We are a species that processes information by what we see. Originally when we came out with computers, it was all text-based. And then we came up with these GUI, graphical user interfaces. It adds so much more requirements on your machine, but it makes these computers a lot easier to use, So we'll look at all these. We'll look a little bit at HMI panels and how they work. We won't get into how they program them. We have it as part of ILT 212, but unfortunately we haven't got the two times that we've taught that class, we haven't been able to get to where they actually do the HMI programming. Syncing and sourcing, we looked at this. We talked a little bit about that. I drew what I was going to draw right here about, well, y'all understand that, right? And so we buy our PLC, and the PLC inputs where we connect the input devices to the program controller has got to run a common. So if it runs a negative common, then that means my sensors have to use a positive common because we got to have current flow, right? If my input runs a positive common, then my sensors have got to use a negative common. That's where the NPN and the PNP sensors come into play. So make sure that you replace a sensor, even if you don't get it from the same company, that you place it with the same type that runs off the same voltage. Normally in PLCs, the predominant voltage on programmable controllers is plus 24 volts. Now, for a long time it was 120 volts because that was all your control logic. What changed this is when the National Fire Protection Association came out with a safety policy that they call 70E. So if you haven't heard of 70E, you'll probably learn about that when you go to work and you go through your safety part of your training. So normally now, when I went to work at U.S. Steel, or even they just stuck us with something. Most companies now, due to suits and insurance and all that kind of stuff, usually the first week you'll be in safety. And but what 70E established was they finally established what was considered to be a lethal voltage. It doesn't mean that you can't get killed with voltages below that. So a car battery can kill you if it gets you in exactly the right situation. Or, if you go in there and fire all your skin off, and you touch your two things on your car battery, you'll probably get enough current flow to hurt you pretty bad. But, our skin has a lot of resistance. It's pretty high resistance. So if we got skin, normally we can get into this without worrying. So I'm not saying that voltages below this level will not kill you. It's just highly unlikely that you'll get killed. So what 70E established, the National Fire Protection Association, 70E, this is a safety standard. So this deals with electric shock, arc flash, and arc blast. They've established that 50 volts is considered, anything above 50 volts is considered to be lethal, which means as soon as you get above 50 volts, you got to add additional PPE. Used to, every time I taught this class and I said PPE, I'd say, does anybody know what that is? And they wouldn't. But now, since COVID's came out, everybody here probably knows that PPE stands for personal protective equipment. So the higher the voltage or the energy level that you go, the more PPE that you have to put on. So anything above 50 volts, below 50 volts, if you work at a company, you'll probably wear rubber sole shoes, probably metal tarsals or steel-toed shoes, long pants. Depends on where you're at. They might require long sleeve shirts or short sleeve shirts, but no nylon. You can't wear any nylon clothing. Normally you have to wear eye protection, safety glasses. They usually provide you with ear protection. It all depends on where you work on. And then out at U.S. Steel, they also provide us with a hard hat and a meter. So they provided us with a meter. So it all depends, but that would be basic safety for most companies. But like I said, that would be something that you would get into when you did your safety training. So 24 volts. So the predominant voltage on current PLCs is 24 volts DC. So it doesn't mean you can't run AC devices. It means 24 volts DC would be the output of our outputs, and then we could run that into a relay. Does everybody understand relays? Anybody got any problem with relays? Do y'all understand those? Okay, so we got something here that shows that in a minute. So we should be okay. So sensors can be either digital or analog. By far, the most sensors out there are digital. Digital means their either output is on or off. Analog means that it gives us a varying input a varying output that represents an input value. I'm not saying you'll not run into analog sensors, because we live in an analog world. Like temperature does, if it was digital and the high today was supposed to be 53 and the low was supposed to be 32, it would jump from 32 to 52 with nothing in between. But it don't do that. Temperature varies slowly. So if I need to, I've got a digital controller on my thermostat at the house. But that sensor is an analog digital sensor. So it actually goes through and varies. But I can set where the temperature, so I've got another sensor where I can set what temperature turns it on and what temperature turns it off. Well, that would be digital, which is pretty neat. So a thermostat, especially the new thermostats, are very, they're very complex. I mean, you can get thermostats now that you can control from your phone. So you can set the temperature through your Wi-Fi. So we got a lot of different things now that's available to us. So analog is out there, and some of them, so we have to handle that. In fact, this PLC right here has two analog inputs, which would be these two at the top right here. I don't know if y'all can read the analog right there. Yeah, I don't know. It's almost, y'all can almost get it. I'm trying to make it focus. This has two analog inputs right here. Now, of course, it's got a common that we use for both of them, and then it's got two analog inputs. So what it does is it takes an analog input and then converts it over to a number that represents that, a number that represents that input. So it's really neat. So I didn't bring in, I don't have our compact logics. Those things have several analog inputs on them, and also analog outputs. So we have several sensors that are analog. We have one sensor on the Amatrol line, which is over on this station right here. And this is one thing we'll do. One of our first classes, and we'll come over here and examine these. It's on this station right here. And this station right here has a suction cup on it. And so what it's got an analog pressure sensor on it, so we can actually measure the amount of pressure that's generating the vacuum. And we'll look at that. You can actually generate a vacuum from a pressure, and we'll look at that and see basically how those things. It's called a Ventura, and we'll look at those. And this is on both these manufacturing lines. It uses a Ventura to take a pressure and convert it into a vacuum. We're going to look at limit switches. Limit switches are contact sensors. These have to actually make physical contact with the device, but when we say sense its presence, we know it's at a certain spot. We know it's at a spot. We don't know where it's at before it gets to that spot, and we don't know where it's at when it leaves that spot. So what these are going to do is they're going to check to see if something's present at a certain location. The first ones we'll look at is limit switches. These are actually contact. These actually, the device, the object that we're trying to sense the present actually has to make physical contact with this sensor. Your proximity, even though that's proximity, by the way, limit switches have been around for years. And they've always been called limit switches. So when we added the term proximity, which means at a certain spot, these have became known for the non-contact sensors. These sensors don't have to make physical contact to see if something is present. We'll look at photoelectric sensors. Both these manufacturers lines. The Festo has a lot more. The Amatrol has a few, but we'll look at what we call through the beam. We'll look at optical interrupters. We'll look at a diffuse sensor, and we'll look at retroreflective. We'll look at inductive sensors. These guys sense metals. So y'all probably ran across an inductive sensor on your way to college, to class, or sometime today. If you got out today, if you drove today, the last time you drove, you probably ran across an inductive sensor. These are the sensors that are buried in the road that senses when your car is present and decides when to change the red lights. So y'all ran into these even though you didn't know it. So these guys sense metal. Capacitive sensors, these guys sense non-metal. They will sense metals, but they also sense non-metals. So these are basically a touch screen is nothing but thousands of capacitive sensors. That's all it is. So You played around with capacitive sensors probably today. If you got a touch screen on your laptop that you're using, those are just thousands of capacitive sensors. And so what they do is they sense non-metallic objects. So of course you are a non-metallic object, so that's what you're doing is you're touching a group of capacitors, and then your computer determines where that group of capacitors are, and that's where it puts your cursor or wherever you want to do. We'll look at reed switches. These guys sense a magnetic field. We'll look at Hall effect sensors. These sense magnetic fields. We'll look at ultrasonic sensors. These guys can be used for a lot of applications. We can sense, basically they're primarily used to sense distance. So we'll look at some other non-contact sensors. We'll look at sensors that sense force, pressure, flow, speed, tachometers, tach generators, incremental encoders, and variable reluctance sensors. We'll look at sensors that sense temperature, thermistors, thermocouples, bimetallic strips. We'll look at sensors that sense position. These will be potentiometers. The Amatro line and the Festo line uses the potentiometer to sense position. So we'll look at those when y'all finally come into campus. We'll look at LVDTs, linear voltage differential transformers. These are used a lot on hydraulic actuators to sense their position, and we'll look at encoders. And the Festo line does not have any encoders on it. The Amatro line does. These are used primarily, they're used for a lot of things. But every robot has one of these guys, each one of these guys on every axis to sense the position of where those arms are at. But we'll look at absolute and incremental. So basically, analog sensors. So this would be like a thermocouple. A thermocouple is a temperature sensor. So we'll look at those. These thermocouples, these are fairly accurate. They're not real fast, but they're fairly accurate. Thermocouples are used in your oven. So when you set 375 degrees on your temperature, thermocouple, these are analog devices, and these are actually measuring the temperature for you, so they're really accurate. If you've got a gas water heater outside, odds are it's got a thermocouple on the pilot light to control the main valve. So analog sensors give us a varying output, so you can understand this is very, very desirable. Most computers, though, are digital. They look for ones and zeros. So if we run this into a controller, then we're going to have to run them through a device called an analog to digital converter. Well, there's an O in there. That's not a B. Now these are pretty popular now on most of your PLCs. If not, you can add them on what we call a rack mount or a modular PLCs. And what this does, it'll take an analog quantity and convert it into a number. Of course, it's a binary number. We're not going to get into that, and then they can use that, and then the programmer could use that value to cause certain things to happen. Then we do have digital. So this is one of the devices we're going to look at. It's called a through the beam. And what they're doing, if you looked at this wheel, it would have a bunch of holes in it. And as this thing spins, every time the light comes through, it will allow the light to be transmitted by the light emitting diode over to this sensor, and it would give us a series of pulses for every one of them. We would bring that into a programmable controller. We'd do a little math. So the programmable controller can't give you RPM, but it's a computer, so it has the ability to do math. So we could count the number of pulses over a second and then multiply it, and we could very easily come up with RPM on there. So that's the kind of tricks that you'll learn on a PLC. So this would be digital. If it was analog, I would get a voltage that represents speed. We do have those. Those are very, very predominant until we came out with these encoders, which are probably dominating speed now. But used to, we just ran a generator that the faster something run, the more voltage it would put out. And then we'd use that. And those are still, you'll probably run into those a lot. But analog, the advantage of analog, so which is more accurate, analog or digital? Well, analog has the ability to deal with infinity. So, like time is analog. Even though we have digital watches, time is analog. And when we get into our field, we understand that because, you know, the normal human talks about seconds. We talk about milliseconds. We talk about microseconds. We talk about nanoseconds. We talk about picoseconds. How far we could go? We could keep going. Because basically, time is analog. There is literally an infinite number of increments of seconds between each second of a clock. But average people can't understand that. So we have a feeling of that when we get into some of our devices. You know, we start talking about some of these devices that respond in milliseconds, microseconds, picoseconds. So what we're doing is we're taking that second and dividing it into all these smaller units. You know, length is infinite. So we talk about milli-inches, micro-inches, nano-inches, pico-inches. So how many spaces, how many dots or increments are there between an inch? Well, there's an infinite number. It's just that we don't understand that. So lengths are basically analog. Temperatures are analog. Light is analog. And so analog gives us the ability to deal with infinity. Digital don't. Digital, we have to decide on a resolution. So you know, digital. This guy right here runs what we call. This guy has a 10-bit A to D converter, which means it can take that voltage and it can split it up to 1,024 different increments. So that's going to be the step. So there's going to be space between each step. The Siemens PLCs that we'll deal with in ILT 212 has a 12-bit A to D converter in it, which means it can take a 10 volts, a 10 volt input, and divide that into 4,096 different combinations. So that has a better resolution, but sooner or later we're going to have to give up on the number of combinations we have. So even though those are not, so digital is no way in the world can be as accurate as analog, because analog allows us to deal with infinity. We can't deal with it, but analog can. So even like I'm talking about, you know, most people don't understand milliseconds, microseconds, picoseconds. They deal with seconds. In fact, most watches now don't even move in seconds anymore. We don't have a second hand anymore. I'm sorry, it moves in seconds, but it don't have a sweep to it. So analog is a lot more accurately, but it's so hard to deal with. It's hard to deal with infinity. So we're gonna have to give up. So digital is either a binary number or it's ones and zeros. So normally when we talk about zeros, digital, we think it's true or false. It's either off or on. So we'll find out that most of our sensors are digital sensors. Some people call them binary sensors. In PLCs, we call it there's a math that we learn in digital. If you take digital, it's called Boolean algebra, and we don't teach it because it would be used for design. So what we can do is we can take a digital circuit and we learn how to write a equation that would represent the circuit. And then what we can do is there's a lot of the rules that you learn in algebra where you can reduce equations. So if we can reduce the Boolean equation for a circuit, it means we're actually eliminating devices in there. But the problem we have is that digital cannot be as accurate, but all we're dealing with is truths and false and off and ons. So it's a lot easier it's more accurate to transmit, it's more accurate to receive, and it's more accurate to store in the memory devices. So this is an example of analog. Y'all all dealt with potentiometers. Today, a potentiometer gives us the ability to connect the output of the potentiometer, whether it's these are rotary pots, but we also have linear pots. So the Amatro line has a big old linear pot. It's laid out like this. And then, of course, we got I'm not drawing this, and then it's got a wiper. Now what happens, you can see it real easy on the analog, on the analog pot, or the rotary pot, is that if we have this wiper connected to something, when it turns, it moves, and it gives us an output voltage that would be proportional to the position of the pot. So we could take that and connect it to something that's in motion, and it would let us know exactly where that device was. So that means if it's coming here and sitting in the center, and then I had this across 12 volts, and this was 0 volts, if it was in the center, it would give us plus 5 volts. Well, that would represent a certain angle. So if we did this was 0 degrees, and this over here was 350 degrees, then if we put it right here, then it would be half of 350 degrees. So we can use these guys to generate an output. We can use these guys to sense position, but it's going to be an analog quantity. So what that means is, if I brought this into a computer, I would have to run it through an analog to digital converter. And it's becoming more popular on the programmable controllers to have these A to D converters on there. This guy right here is called induction. Let's go ahead and take another break. I'm going to go over and get this thing so I can show you induction. And so we'll be back at, 7:32. So the three things that's required to induce a voltage, let me get back to our PowerPoints, is number one, we got to have a magnetic field. Number two, we have to have a conductor. And number three, we have to have motion between the two. What determines the amount is the strength of the field, the number of conductor loops. So we loop the conductors, and you can see this on my basic little transformer here. And the loops have to be in the same direction, by the way. And then number three would be the speed of the motion. Now this is why it doesn't work with AC. So AC is doing this. So that means this would be a pot. We call this an alternation. Starts at 0, comes up, swaps directions. So when we run current through a magnetic, and I don't have my electromagnet, we call them electromagnets, guys. So when I run current through a conductor, it generates a magnetic field. Well, what happens on AC is the field would build up, and then it would collapse, and then it would build up again. So AC automatically creates the motion. Putting current through a conductor creates a magnetic field, and then we have a bunch of conductor loops. So what I have, and what's neat about DC, is we can actually take DC and convert it back to AC. So this is what you can go out and buy what we call an inverter for your car, where you could hook it up across your battery and you get 120 volts AC out of it. In fact, my wife's van, she's got a town and country van. It has a regular 120 volt AC outlet in her van. So the grandkids can come in and plug in their cubes in there and charge their phones and stuff like that without having to use the USB. So what we have is here is we have AC. So this is a function generator. So it's taking we're taking AC, we're converting it to DC, and then we're electronically converting it back to AC. So this is AC. I have my thing set up to generate AC. And now we can set the frequency, the speed of the alternations. We call this is we got this set, and we're setting speed because we have very very low coupling here. So I've got it set at 5 kilohertz. I got it set at a little over 10 kilohertz. So what I have here is I have 2 coils of wire, and right now they are not connected to each other at all. So here's one. This is connected to my function generator. This is connected to my light emitting diode. And what I'm going to do is I'm just going to come up here and lay this on top. And hopefully you saw the LED come on. I take it up, it goes off, it comes on, it goes off. That's magic. They're not touching each other. This is what we call induced. We're inducing a voltage into this guy, which would be what we call the secondary, with a magnetic field. Now we have a very poor coupling. This is using regular wire, so normally we have magnetic wire. Should have brought it over here. Magnetic wire has a really really thin coating on it, and then we put a iron core in it because iron concentrates magnetic fields. So we can increase the strength of the magnetic field by increasing the coupling. And on a transformer, the conductors are actually wired directly on top of each other, depending on what type of transformer it is. So we have a really good coupling to transfer that thing. So the strength of the magnetic field, and this is the way an LVDT works, is we change the core, that piece of metal that's concentrating the magnetic field. So what happens is what we're trying to measure, the actual position of, is actually moving the core. So the device I'm trying to measure moves the core. And what happens is if it moves this way, it couples better on this side. If it moves this way, it couples better on that side. So it gives us out a signal depending on its left and right. These are used so if you looked at them, they look like a lot like a shock absorber on a car. If y'all ever seen a shock absorber on a car, they look. So we seal them up really nice. We run into a lot of these on hydraulic systems. They're very very rugged. And what we do is we get a differential voltage depending on where the core's at. So what it's doing is changing the strength of the magnetic field on these transformers. So here's the primary, and these two are secondaries. So if we move it this way, this guy here has more metal, so it would output a higher voltage. If we move it this way, then this guy would have more metal in it, and it would output a higher voltage. And we sum them together, and we end up with that. And these are called LVDTs. And like I said, the only place I've ever seen them hooked up to is actually actuators on a hydraulic system. Because hydraulics we can't do what we do. We'll look at position sensors on our manufacturing lines, and they use magnets. I mean, they use magnetic sensors because it's pneumatic. So pneumatics, our cylinders can be made out of aluminum, and magnetic fields pass through aluminum real well. Hydraulic cylinders are going to be made out of steel because the pressure is so high. So that means the magnetic, if I try to sense a magnetic field connected to the piston of a hydraulic cylinder, the magnetic field wouldn't get through. So if we connect the LVDT to the actual rod out there on the output of our cylinder. So when we talk about a cylinder, they're round or square. They're all round. And then we come over here, and this would be the piston, and this guy coming out would be the rod. And then what we do is the LVDT would be connected out here. And now we can sense the position of the rod, which would give us the ability to bring that into our controller, and we can actually sense position. So we'll show y'all some hydraulic cylinders, and we'll look and see how, not hydraulics. Ours are all pneumatic, which means it uses gas. So hydraulic means it uses a liquid as a fluid. Pneumatics means it uses a gas. And of course, the predominant gas is air, even though air is a combination of gases, which is readily available. But we can't generate as near the pressure with pneumatics as we can with hydraulics. So these are called optical encoders. We have several. We have one of these on the Amatro line, which is the one we're going to spend most of our time with, because we've got all the documentation that goes with that line. We have the electrical prints. We have the we don't have the PLC programs written out, but this is the line we'll be spending most of our time with. And it's got one optical encoder that's on a conveyor belt. What we have is we have two types. We have one we call incremental, which is probably the most popular, and then we have what we call absolute. Absolute deals with a number system called binary. So this has 1, 2, 3, 4. So a binary, we would start counting. So this would be, by the way, it goes 1, 2, 4, 8. So this right here would be a 0. If I come up here and did that, then it would be a 1. If I come up here and did that, then it lines up with a 2. If I come up and did that, that's going to be 2 and 1. That's going to be a 3. This would be a 4. This would be a 5. This would be a 6. This would be a 7. This would be a 8. This would be a 9. This would be a, this would be a 10. This would be 11, 12, 13, 14, and 15. So what we have is we have these photoelectric sensors. Basically what it does, it shoots a light beam, usually using an LED. And down over here it's got a receiver that every time the light hits it, it gives us a digital pulse. But what happens is that these are actually going to give us a binary number depending on what lines up. So right now it looks like we got this one on, this one on, this one on, and I can't see what's going on here. But if all of them was on, that would be a 15, which means we were at position 15. These are called absolute encoders. The problem we have is the more digits we have to add more bands. So if I want 15 combinations, 16 combinations, if I added another band, I would get 32 combinations. And so the preciseness or the resolution would go up. I would be more accurate on my spots, but I keep adding bands. On an incremental encoder, all we do is get a series of pulses. And then we run this into a counter. Your PLCs, one of the main things they've got is they've got counters. So what we would do is we would bring these pulses in and we would count them. And then we could use that to sense position depending on a number of counts. The only thing we have with incremental encoders is that you have to start them from a 0. So this is what the robots use. So we call it origin. So you have to start counting from 0. So if you got a printer, at your house, not a laser printer, an inkjet printer, you notice when you turn it on, if it's out somewhere, it'll go over there and find itself over on the left-hand side. Well, what it's doing is finding 0, and then once it finds 0, then we can send it counts to cause it to move across. So that's the only big disadvantage of a incremental encoder, is that if we lose power to it or something like that, we lose our count, and we have to have a 0. So on robotics, you'll hopefully, especially if you take operation or programming, or if you take projects, you'll learn how to origin a robot. And what you're doing is you're setting 0. And what the robot has, it's got a set of batteries that are actually in the robot, and that way it won't lose 0 if we lose power. But you got to keep those batteries up. So if the batteries go dead, this happened on the big Fanuc, by the way, the big 430 IW Fanuc, it lost its position because we didn't change the batteries out. So we had it uses regular D-size batteries, which is pretty neat. We replaced the batteries, and we had to reset 0. So it's got marks on the robot that hopefully they'll show you all that and maybe let you reorigin a robot. And what you do is you move it, or we call it jogging. You move it to those marks, and then you set 0 on that. That's called a rough 0, but usually that's good enough to get you back where you're at. You're going to be within, a millimeter or so. If you want it, if it's got to be precise, then what you do is you have to buy a special calibrating jig that you put out on the tool. So you'd have to take the tool off and mount this thing on it, and then you move it to a certain position to set what we call a precise 0. We had this happen on the Festo line, which has a robot, and we had a little problems on that because Festo decided to redo the origin when they put the Mitsubishi robot on there. They decided to do the origin a different way. So when I got back, when I had my motorcycle wreck, I was out for a year and a half. Well, the Festo line was turned off for a year and a half. And so when we got back, the batteries had gone dead, and the robot had lost its 0. So we set the origin according to the textbook, according to the book that came with the robot, and it missed all the spots. So we called Festo and found out that they had a special jig that you had to put and move the robot to a certain location to set the origin. So they redid that. We've had to do that twice, by the way, because it's lost its origin. So you have to watch out for that too. So we finally got it back up and running, and keep good batteries in your robot, by the way. So this is and by the way, what we do is most of the time on these incremental encoders, we have 2 sensors, and the sensors are offset by about 90. These are set off by about 90 degrees. So what that means is that if we move in one direction, then one sensor will pulse first. If we move it the other direction, then the other sensor will pulse first. We call these quadrature incremental encoders. So not only can we get position, but we can also get direction. So on a robot, we got to know which direction it's going. So it tells our counters either to count up or count down. So what sets the resolution of these guys is how many digits your counter can count to. And also you got to keep those batteries on the robot. You got to make sure you change batteries. In fact, on the big Festo, you open the door on the controller, and they got a service thing on there, and they actually document every time they change those batteries, and they change them out every month. And they're 4 big D-size batteries. They probably last 2 years, but they made sure they didn't do it so they wouldn't have to reorigin the robot. So the advantage of an incremental encoder is that it's very the resolution is a lot better. We don't have to add more tracks for that. It all deals on basically how far can your counters count up to. So over here on the left, go ahead. Yeah. No, what you do is you usually hit e-stop, but even on a robot, when you hit e-stop, it does not remove power from the. It usually energizes the brake. So what you do is you change the batteries. You change the batteries with power on. So, and by the way, if you never turn the robot off, then you'll never use the origin. So the batteries are only used when the robot is turned off. So that's what you'll find out right off the bat is that when they did that preventive maintenance, they changed those batteries with power on. So, but they hit the e-stop, which don't take power. It removes power from the servo motors, but it does not remove power from the encoders. So that's a really good question. But you're right. If power ever fails and the batteries are dead, then you lose your origin. But if power never fails, and that's the problem that we have, is that some of the batteries, of course, the big FANUC only uses D batteries, and they're not very expensive. The Motorman robot uses C-type batteries, so it's not. I'm sorry, the Festo. I'm sorry. The FANUC the small FANUC uses C-type batteries. All the other ones use specialized batteries, and they're fairly expensive. So we usually don't change those out because we know how to origin the robot, and it's good practice also for the students. So I think the batteries for the ABB robot seems like they were like $240 for those. And we had to get those. We had to get those from ABB. The one for the KUKA and the Motorman, we carried those down to over to Batteries Plus. I think it's called Batteries Plus Lights or something like that now. And they were able to give us the batteries, but they didn't have the right connectors on them. So we just moved the connectors over. So we were pretty lucky on those. But we can't do that on the ABB robot because Batteries Plus don't have those batteries, and since they're lithium batteries, they don't want you to solder on lithium batteries. So they had the right size, but you had to solder. They had no wires on them, and you had to solder them on yourself. And y'all know what happens when lithium batteries get hot, right? They catch on fire. So those hoverboards started having a big problem where they didn't have the right charger to charge them, and they'd get real hot and they'd catch on fire. I don't know if y'all probably remember those. But you can look, this is an absolute encoder, so it's got 1, 2, 3, 4, 5 bands on it. So that would give us a count. We'd have 32 counts. I'm not going to tell you how I come up with that. It's just I know a lot of stuff about that. So if I wanted more counts, I would have to add another band. So now it would get bigger. Also, normally we have an index hole somewhere where we know when it gets 1 pulse per revolution. So it might count to 32, and then when it got that pulse, it would know it needed to count from 33. So there's a lot more to absolute encoders. What's nice about absolute encoders is that if you lose power, you turn it back on, the device knows where it's at. The problem with incremental encoders, if you lose power to the encoders, then you lose your origin, and you have to redo that. Of course, your printer does not have batteries in it, so that's why if you lose power, you'll hear that thing find 0. You ever done that? So like when you place the cartridges on it or something, or you turn it off and turn it back on, it'll go over there and seek over to the left-hand side, and then it'll come back out. Well, that's what it's doing. It's finding its 0. It's reorigining itself. Of course, we couldn't do that with robot. The first one that we had was a Rhino robot, and it had limit switches on it. So if it ever lost its zero, it would just jog itself until it hit the limit switches, and then it would come back if we told it to origin itself. It was pretty good. That was the first robot we ever had, by the way, and that was one of those where they bought it, and they told me it was here, and I had to figure out how to program it. So that was interesting. And it didn't have any program. It didn't have a programming application. So I had to write the programs in a language called BASIC. If y'all ever heard of that language, Visual Basic is still it's the newer version on that. But if you ever played around with Visual Basic, you get a basic feel of the basic program. But Visual Basic added the ability to add graphics or graphical user interfaces in there. So proximity sensors, we have limit switches, which are contact. We have several of these on both lines. The Amatro line has more. These guys have been around a long time. Photoelectric, both the lines have photoelectric sensors on them. The Amatro line has diffused, it has through the beam, and it has retroreflective on there. And then the Festo line has both of those. So we'll look at those type. Magnetics, both of them have magnetic reed switches, and both of them have Hall effect senses. These guys sense magnet. Inductive sensors, both of them have inductive sensors on them. These guys sense metals. These guys sense magnetic fields. These guys sense light. This guy senses non-magnetic. We can't say non. It does good with metals. So it senses basically it senses just about all solids. And also we can sense liquids with it. Of course, none of ours do that. But capacitors, they'll sense plastic, they'll sense metals, they'll sense almost anything. Of course, ultrasonics, these sense distance. We can also use them to sense speed. So if we send out one pulse and then a precise amount of time after that we send out another pulse, and we know the speed. So this is the way radar works, guys, is like the speed detectors that the radar guns that they use on some police use, is they shoot out a pulse, it bounces back off your car, they shoot off another one at a precise amount of time and see how far you've traveled between those two times, and they calculate your speed. Of course, we also have photoelectric, which deals with reflective light. So it's lasers what they're doing. They're shooting a laser beam, and it works on the same principle. They shoot a beam out, and they count. The sensor basically calculates how long it takes to reflect back. Of course, ultrasonics or radars. You can sense those with radar detectors. The infrared are a lot harder to do. The term limit switch refers to a contact electromechanical device that senses proximity. But this guy was first called a limit switch. So even though it senses proximity, it's got the name limit switch. So now when we use the term proximity, we're talking about non-contact sensors. So a limit switch is a contact sensor. It's got to make contact to sense when something is at a certain spot. Where non-contact sensors don't have to make contact. They use some other means to do that. So these are limit switches. This is pretty obvious how they work. So what they got is they've got an operator. The operator makes physical contact. It causes contacts to change positions. and it gives us a signal that we use to know when it's in. So the position of these would be critical. We've got these. We got I don't know how many on the Amatro line. I know we have at least 2 on the Festo line. I think we got like 3 or 4 on the Amatro line, which is to be the one that we don't have these big ones. Like I said, these things have been around for years. They're very, very rugged. Uh, the biggest problem we have with them is they're electromechanical devices. So that means they could fail mechanically or they could fail electrically. The biggest problem we have is people not mounting them correctly, and they exceed the range of the operator, and it breaks off, or they bend it, and then all of a sudden it's not good anymore. Also, when they wire it up, they'll move these covers. These covers have a nice rubber seal in them to seal them up. It's down here where the wire conductors come in from the bottom. It's got a assembly that clamps the wire in. It's got rubber on there that allows to seal it up. What'll happen is we'll get somebody out there. They'll take off the cover and they won't screw it back on, or they'll leave it off completely. And then they're out in industry and you get all kind of goop in there, or they don't seal up the bottom correctly. So corrosion gets inside of them, or they try to get too much current out of them. So we have different sizes, right? And we have different operators that we can. We have rotary, we have plunger type, which means the actual device would come up here and would push in on this wheel, and it would move down inside the limit switch, and all of them. In fact, some of them you can this unit right here, you can actually take this off and replace it with one that handles this guy right here. So a lot of the limit switches can be reconfigured to be either rotary or plunger type. These guys, like I said, these are compared to solid state or electronic sensors that are a lot cheaper. As long as you maintain them and don't expose them to something they're not supposed to be exposed to, they last a long time. And of course, their big advantage, of course, is they're cheap. So if they can use one of these instead of a photoelectric sensor, which basically you have to keep clean, then they're going to use one of these. So these work in harsh environments if you keep them all sealed up. These are the ones that we have on our manufacturing lines. In fact, most of them we have are these electronic duty, or those guys right there, where they have a wheel on there. Then when it hits the wheel, it pushes it down, and then it's got a little operator right here that actually energizes the switch. These are usually so on switches. So y'all probably need to know this. So this would be one type of switch. So let me do it like this. Now we have a term. We have poles. Poles are the number of switches controlled by a single operator. And then throws would be the number of positions the switch would do to control a circuit. So this right here would be called a single pole, single throw. Or SPST. So if you ever go a light switch is a single pole. Most light switches, if you got a two position or where you can turn the light off or on from multiple places, those are single pole double throws. And I can show you all the circuit. But if you go out there to like Lowe's and you pick up a set of regular light switches, odds are you're going to see that SPST on there somewhere, which means they're single pole, single throws. If we come over and do this, so this is what we have that controls lights that we can have. So here we have one switch control that we can put in two different positions. This would be called a single pole double throw, SPDT. So So this is the way this is the one they use. By the way, electricians don't call it a single pole double throw. They call it a three-wire switch. Or three-way. They call it a three-way switch because it's got three wires connected to it. I guess that's how it got the name. But these are single pole double throws. So what we would do is we would come over here and we would come in on this one. And then we'd run these two wires. And then over here we would hook this one like this. And then our light bulb would be right there. So right now the light bulb would be off. If I flipped it up to this position, the light, if I flipped this one up, then the light would come on. I come over and flip it down here, it would go off. If I flip this one down, it would come on. So these are your three-way, they call them three-way switches, but they're actually single pole double throws. So that's the circuit on those switches. If you get past 2, you got to go to a weird switch. It's not, we don't have a nomenclature for it, but it would go in the middle. They call it a 4-way switch, by the way. So that's a light that you can control in 2 positions. Most houses have it. We got one on our hall. We got the hall that runs. I have a single-story house, and we got the hall that runs and connects all the bedrooms together. We got them on both ends, so we can do that. If I come over and do this, and then I come down here and do this, and then I put a dash, it means these are connected together. So we got 2. So this would be a double pole, but each switch can only control one circuit. So this would be a double pole single throw. If we come over here and do this, and we come over here and do this, then this is going to be a double, and we put the dash line, by the way, indicates they're connected together. They're operated by the same operator. This would be a double pole double throw. And that's about as far as we get. After that, we go to a selector switch. So normally these guys, you see this guy's got 1, 2, 3. So that means this has got to be one of these guys right there, a single pole double throw. Every one of these. So this has got 3 connectors. So this would be a single pole double throw. Normally it'll be on the side. If it's not, you can use an ohm meter. Looks like this is the common, and these would be the 2. This has 3 wires. This one I only see 2, so that's probably a single pole single throw. And this is a single pole double throw. This one looks like it's got 3. But you can see these are plunger types. These have a little wheel on them. But these are what we call electronic duties. These are used a lot on PLCs because PLCs don't require very much current on the inputs. But these right here could actually run a load. So we could run a load off these big heavy duty limit switches. But you'll run into a lot of these in PLCs. So normally what we would do right now is we'd go over to the manufacturing line and we would allow y'all to look for these different limit switches. So this will be something that we'll have to do when y'all come in on next Tuesday. We're coming on campus next Tuesday. We will not be virtual next Tuesday. Odds after that, huh? Oh, I'm sorry, wrong class. Monday. This holiday's got me off, by the way. We were off Monday for Martin Luther King Day. So Monday we're gonna be. Thank y'all. I'm just seeing if y'all's paying attention, right? So Monday we're gonna be on campus, and we'll probably be on campus the rest of the term because we got plenty of space to social distance in the room that we're in. We're in H111, which is in the Ethel Hall Building of Automotive Excellence. We're down on the bottom floor with the tree. So we got the tree out front. So before, you can't go out the south gate anymore anyway, the one that's closest to the Bessemer Civic Center. So if you come all around the campus, and before you go out the south gate, the one that doesn't have the red light, we're on the right. It's got a tree out there. And my Jeep Compass, by the way, I don't have my HHR anymore. I got a maroon Jeep Compass, and that'll be sitting out front. So a couple things that we're going to do, so I need to remind me, is one of the first things we're going to do is we'll go over lockout tagout again, and we'll all do the lockout tagout lab. And so what that means is, once we do that, every time you actually work on your module that you're going to be assigned with a person, then you will, both of you will lock out and tag out. Not when you're only when you're working with, not only when you're troubleshooting, but when you're actually working on something, right? Normally when we troubleshoot, we don't lock out, tag out, because we've got to see the thing operate. We're going to have to take voltage measurements and that kind of stuff. But it's actually when you get in there and start replacing parts, that's when you need to lock out, tag out. All power sources, right? So non-contact proximity switches. So another thing we'll do is we'll go back through here and let y'all identify or try to find these sensors on these manufacturing lines. What we'll probably do here is we'll let one of y'all be in front of the module, one of them y'all be on the back of the module, and then y'all will tell your partner what you can see, and they'll tell you what you can see, what the other one can see. So that way we can be, social distance. By the way, you are going to have to wear a mask. You are going to have to wear a mask. And at the end of the class, we'll have to leave enough time so we can sanitize. So we got the sanitizing wipes and everything where you'll have to wipe down your station. And then we got some spray where you can spray your chair off before you leave for the next class. So the first proximity sensor we'll look at is the sensors that sense magnetic fields. These are going to be your magnetic reed switches and also your Hall effect. We've also learned about another sensor that I didn't even know about. It's called a magnetoresistive, but it works very similar to a Hall effect. It's just that one of them senses horizontal magnetic fields, and one of them senses vertical fields. So odds are, when you buy these, you'll have to make sure you get the same type because of the way the sensor is actually mounted to detect the magnetic fields. So magnetic reed switches, these are contact switches. Contact's closed when the presence of magnetic field, has an electrical contact. Pros, it's very cost effective. Does not have to be powered to operate, but it's electromechanical. Now, as soon as we say electrical mechanical, it means that the device can fail two different ways. It can fail electrically or it can fail mechanically. It's like your car or the vehicle that you drive. It's electromechanical, so it can fail two different ways. You can have a flat tire. Well, that's a mechanical failure. Or it could have an electrical failure. It might not start, or one of your lights might burn out. So anytime we deal with two technologies, it means two devices can fail. So this is basically what what a reed switch looks like. And I'll have to show y'all these when we get in here. So y'all need to make notes. So a reed switch is basically and we use drive contacts. We don't need to use this, even though mercury switches are still used some. But we're going to use this dry contact. These are the ones that's on our manufacturing line. And we have several of these. And I'll show you how you can identify them by their symbol. So what we have is, this is inside a vacuum. And what we have is we have a contact that's very, very close together. But it starts off as being open. So we would call this normally open. So this would be a normally open contact. So what happens is when we come up here and we expose this to a magnet, so you can't put the magnet in like this. I actually learned this. I was wondering why I couldn't make it work, and then I realized what I was doing. So I've learned a lot. So we can't do it like this. So what we have to do is we have to put it like this. Now this could be south and this could be north. That's not the problem. So what happens is the magnetic field comes up, concentrates to the metal, comes over here, and now what we have is we have a north sitting right here, and we have a south being concentrated to the metal that's sitting right here. And like magnetic fields attract each other. So what would happen is it would cause the contact to close. And it's really cool. I mean, it works really, really well. And so if you bring the magnet in like this, north south, or you bring it in south north, it don't work. But you could bring it in north south or south north, and it would work. So these guys are, like I said, there's almost nothing to them. We use these on sensors. If you got a burglar alarm on your house and you got these sensors that you put on your windows, we have the reed switch is the one that's mounted permanent, and then that other thing is nothing but a magnet. That's all it is. And so we use these in alarms. We use these to sense when magnets are certain places. And we'll show you all this. So what we can do with pneumatics, so every one of our cylinders on our manufacturing lines has this feature. So basically, the way a cylinder works is that it depends on what they are. So we got two ways. We could come over here and we have a piston, and then we have this guy right here. We call this the rod. So the rod connects to the piston, and which basically is the same thing we call on a car. And we can put a spring over here. So let me draw this in a different color so I can erase it. So we'd have a spring over here. And then what I do is I'll come up here and I'll put pressure here. This will cause this to extend. But notice the piston has a watt on it. It has a magnet. So what I can do is I can place my reed switch in here, and I can tell when the piston is retracted, and I can put another one over here, and I can tell if the piston is extended, because it's pneumatic. So what's nice about pneumatics is that the actual cylinder itself can either be made out of plastic or it can be made out of aluminum. And aluminum allows magnetic fields to pass through them. So all our cylinders that we have are made out of aluminum. And so what we do is we strap these sensors up here, and we can tell when it's extended or when it's retracted. This is called, by the way, this is called a single acting cylinder. Now it's round, but a lot of times they'll take the cylinder and they'll mount it in a square housing, and then they'll put grooves on it and stuff where we can mount these sensors on there. So on a single acting cylinder, what we do is we use pressure to cause it to move in one direction, and then something else brings it back. This is what if you got a hydraulic jack, it's a single acting cylinder. So what we do is we use pressure, and then when we open up the valve, we use gravity or the weight of your vehicle to bring it back. So that's a single acting cylinder. A double acting cylinder would be a cylinder. So we'll redraw the same thing, and then we'll draw the piston, and then we'll draw the rod. Now I'm not erasing that. And then what we do is we have a inlet right here, and we have an inlet right there. So what we'll do is we'll come up here and put pressure, and it will cause it to extend. and then we'll take this pressure off, and then we'll put pressure right there, and it will cause it to retract. So these are called double acting cylinders. And we have both of them. And then what we do is your controller needs to know when it's extended to know when to do the next thing. So it would be awful if something happened and the thing didn't extend it and we was using a timer or something like that. And it says, oh, after 3 seconds, do this. Well, the problem is the thing wasn't extended. So what we can do is we can come up here and put these Hall effect sensors right here. And then the piston itself is magnetic. And now, and of course it's north-south, so it's in the right orientation. And now we can tell when it's fully extended or fully retracted to decide when to do. So every one of the cylinders, every one of the cylinders that we have on the Festo line and the Amatro line have these. They either have Hall effect or they have reed switches, and we'll look at the difference in a minute. So reed switches are very simple. They're going to be 2-wire sensors. The numbers are going to be 1 and 3. They're going to be red and it's going to be blue and brown. Or no, I'm sorry. I need to look at that. I think they're blue and black. But we'll look at that, the 2 wires. And that's one thing we need to know too, is what's the industry standard for these color wires. So double acting cylinders, we use pressure to not only extend it, but we also use pressure to retract it. Single acting cylinders, we use pressure to extend it, and then something else retracts it. Every one that we got uses springs, and it's real easy to tell which one is which, especially when we look at the valve that's controlling the flow of the air that's going to that. So now that we've got these cylinders that's got these magnets built into them, then now we can use reed switches or Hall effect sensors to tell if it's fully extended or fully retracted, or we could actually use it to tell if it's in the middle. But we'd have to have a special valve that controls this to stop a cylinder in the middle. And we'll see how they do it on they cheat on the Amatro line. They do it kind of not the way that they should have done it, but the way they did it actually turns out to be cheaper. So we'll look at the valves that actually control this flow of the fluids when we get in a little more in detail. So that was a magnetic reed switch. So then we have what we call Hall effect sensors. These senses the strength of the magnetic field. They can either be digital or they can be analog. All the ones that we have are digital, which means they either turn on or turn off. These are solid state devices. So since they're solid state devices, they have no moving parts. But since they're solid state, they're going to have to be powered. So they require a power source to operate. And they will drop a voltage across their simulated contacts. So these contacts in these sensors are not true mechanical contacts. They're done by solid state devices like bipolar junction transistors or some other method. And so solid state devices will never drop 0 volts when they're closed, which is what a mechanical switch will do. And we do that all the time. So if I've got a mechanical switch, and then of course if it's open, we will measure the source voltage. If we come over here and it's closed, if it's a regular switch, it will measure 0 volts. Now there's some resistance in there, guys, but we don't have. Well, it might be dropping 1 nanovolts because there's no such thing as something that has 0 resistance. But we don't have the meters that's got the capabilities of measuring that. The best we can do is millivolts. Some meters will measure microvolts, but it'll still measure 0 on our meters. So we look at that all the time, and And there'll be a question on the test, by the way, is how much voltage should you measure across a closed switch with 120 volts applied? Somebody in this class is going to say 120 volts. And of course, that's wrong, so you'll miss that one. So I've told y'all the answer to that question because that's very important to know, because that not knowing that could get a person killed. So you could go over there to a light switch and you measure across it, it measures 0 volts, and you say, well, no voltage there, and then you stick your hand in there, and then we talk about you in the past tense. So Hall effects, these are solid state. These are solid state devices. So what they're going to do is they're either going to use an NPN or a PNP transistor. And these guys here won't drop. They won't drop 0 volts because they're semiconductors. But they're going to drop, it's usually less than a volt. I'm running out of space, guys. My fingers hit my... But these guys will drop a voltage because they're not a closed switch. We're simulating contacts. So this is kind of like Hall effect. Hall effect sensors. So this is the Hall effect sensor. It's going to be electronic. So we got to have at least 2 wires to power this thing up. So these are going to be 3 or 4 wire sensors, and we'll talk about that in a minute. Reed switches are going to be 2 wire sensors. Hall effect are going to be at least 3 wire sensors. It could be a 3 or 4 wire sensor, and we'll talk about what the other wire is. And then we're going to have one more wire that is the actual signal. So these are going to have to be powered. Now, we can make a Hall effect appear to sense metal by doing what they're doing here. So here's the magnet. Here's the Hall effect sensor. And then we roll a metal ball across it. Well, what happens when the metal ball comes across, it concentrates the field through the magnet, and the Hall effect will pick that up. So we can buy Hall effect sensors that appear to sense metal, but they do it with having they have a magnet inside of them, which is different. So this is true. So a Hall effect sensor itself cannot sense metals. It senses a magnetic field, but we can make it look like it, right, by putting a magnet inside the sensor itself. But they're definitely going to be 3 wire. So here we got to perpendicular. So the magnet has to be perpendicular. So that's one difference between a Hall effect. So a magnetic reed, they got to be parallel. A Hall effect, they got to be perpendicular. Of course, we could mount it different, but so this is one big difference. And we got to have power. Power, and then plus the signal wire, and then the signal wire's got to have a common. So we'll look at the color codes, the standard color codes on this in a minute. So that's important to know too when you wire these things up, and they're not the same what we use over here. So what we would do now is we'd go over there and identify all the Hall effect or reed switches. We don't know what they are until we look at the prints, and we'll show y'all the actual symbol that we use on the prints to represent these. But the Hall effect, the reed switch will only have 2 wires when we look at the diagram, and then the Hall effect will have 3 wires. But besides that, the symbols are the same. So we okay? And by the way, a magnoresistive would detect this. A magnetoresistive would detect a horizontal field and then a Hall effect. So it works kind of like a reed switch. So that's one of the big difference between these two, but they're both 3 wire sensors. So I didn't learn about magnetoresistive until I went to a thing with Festo. So Festo brought that out to me, and I said it sounds like a Hall effect. It does the same thing, and the guy says no. One of them's a perpendicular field and one of them's a horizontal field, similar to a reed switch. but both of them but I'm sorry, Hall effect and magnetoresistive. These are electronic, so they've got to be powered up. And it doesn't make any difference. It's just that you got to make sure you replace it with the same type. So if you had a magnetoresistive sensor and you replaced it with a Hall effect because it was similar, then it probably wouldn't work because the magnet field that it's detecting is not oriented correctly. So photoelectric sensors, we have tons of these on both manufacturing lines. Detects the presence of an object using a light source and a light receiver. So basically what we're doing is these are non-contact, they're solid state, they have no moving parts. So they're kind of like the Hall effect. So the Hall effect has no moving parts, so it's electronic, so it can only fail one way. A reed switch is electromechanical, so it could fail two different ways. So solid state, but reed switches are cheaper than Hall effects. So it's a one and the other. And like I said, we have both of these on our lines, and I'll show you how to identify these. These require clean environments. So I think we got one a group from Broza, and it says that's one of their main jobs is to go out there and clean off the lenses on all these photoelectric sensors, even though it's a pretty clean environment. Somebody. Huh? No, it probably wouldn't work at Lehigh. So you've got all type of dust floating in the air there. I know a couple of places at U.S. Steel it wouldn't work either, because they got uh, yeah, out at U.S. Steel we had a lot of graphite, which is black. The results of rolling steel and stuff like that. So no, these guys wouldn't work out there. They might work in some of the new places, but I don't even think they would work at the pipe mill either. So we'd have to use some other type. But in a real clean environment, like a lot of these places we have around here, I've been into car repair shops like at these dealerships, and you walk in there and it's cleaner than my house. So even around here, so yeah, but like Broza, people that does pressing and stuff like that, where it's a real clean environment, then these guys here work great. But like you said, Lehigh, you would have to use some of these inductive sensors or some of these capacitive sensors, or even Hall effect. You might run into some of those in your automation, but I don't know. But that's a good point, Lee. So these are photoelectric sensors. So they come in different shapes and categories. And like I said, our manufacturing, we're in a very clean environment here. So we got one manufacturing line that assembles a directional control valve, which we'll look at. And then we got another that's the Amatro line. And then we got the other manufacturing line. It assembles, they're not manufacturing line, they're actually assembled on. Well, the Festo line simulates manufacture, and it actually simulates actually drilling a hole through a device. Even though it don't do it, we don't bring it down because if it got into the cylinder. So the Festo is probably a manufacturing line. The Amatro is an assembly line. So that's, by the way, that's what Mercedes is down here in Vance. It's an assembly line. So they don't actually manufacture. They get parts from different companies. We call them tier 1 manufacturers. So that's your Broza, your Flexingate, your Gas Stump. They do different things, and then they sell their parts to Mercedes, and then Mercedes puts everything together. So they're basically an assembly line. So we place more people in the tier 1 manufacturers than we do in Mercedes. In fact, Mercedes they decided to sign a training agreement with Shelton because it's a little closer. So, but it's over a 3-year program. Even to get a chance to work in the plant, and there's still no guarantee, guys. So we have what we call a diffused. So a diffused sensor depends on reflective light. So it's actually reflecting light off the object itself. So these would be these would depend on the color. By the way, most of these have what we call a sensitivity adjust on it. So we talk about black, but there's really no such we don't know solid black. So that means even black reflects some light. But you got to have the sensor's got to be really close to it. And then the lighter the color, the more light it does reflect. So the problem we have with diffuse, but so we could use it to sense shades of gray. They're not actually sensing color; they're sensing shades of gray. So the Festo line, some of the diffuse sensors, we have them adjusted so they do sense black, but the sensor is very close to what it senses. And then sometimes we have them adjusted so they don't sense black. So I'll show y'all that, and it puts the cylinders together differently. If it's black, then it's the other two colors, and we'll look at those. But that's what diffuse sensors depend on reflective light. So we have diffuse sensors on both the Amatrol. We have one diffuse sensor on the Amatrol line, and then we have we have several diffuse sensors on the Festo line. And one of the things that the Festo line does is sense when we adjust it to see black sometime, and then we adjust it not to see black sometime. The Amatrol line, it uses the sensor to sense the very first magazine, or actually feed magazine. It's mounted down here, and the problem is some of our plastic sensors has a black RFID tag on it, and the problem is if you drop it into that slot and that black is down toward the bottom, it thinks there's nothing in there because that diffuse sensor cannot see black. I haven't decided. I haven't had. Well, it's good. It's also good for troubleshooting. So that will be one of the problems that we have is that I shouldn't have told y'all that, so some of y'all will find it. But yeah, so that's something you got. So all these sensors, all these blocks, it's got the RFID tag on it. We have to make sure that we come up here and put the RFID tags up. So they're little circles. Radio frequency digital, let's say RFID tag, identification tags is what they are. This is what we call a retroreflective. So what happens is you have a retroreflector tries to return light from the source. So if this was a mirror and I brought a light in on this angle, then it would reflect back. And they call it the angle of incidence is equal to the angle of reflection. But if we got what we call a retroreflector, if you're within a range, it'll hit and it'll come back to the source, which is pretty neat. So you see retroreflectors all the time. They put retroreflective beams on a lot of your stop signs or signs, so you're off to the side and you still see it. These little things they put down the interstate that bounce back to your lights. Your lights are going out, but yet they bounce back to you, so you can see those retroreflectors. They have glass beads that they'll put on the stripes, which are retroreflective too, and they'll bounce back to you as long as you don't exceed what we call the viewable angle of reflection. So that means these reflectors don't have to be lined up perfect. In fact, if you take the sensors class, we have a retroreflector that's AUT 232. It's coming up in T2, but it requires motor controls right now. That we can put that thing on there and we'll start moving back, and you won't be lined up. You'll be off a little bit, and it still triggers it. So that's what's. And in fact, there's a retroreflector on the moon that they shoot a laser beam up to it. For one thing, they use it to measure the distance to the moon. So they finally realized that the moon is moving away from us a couple of centimeters every year. So, huh? Yeah, it's after, but yeah, but you have to have motor controls to take it because it's what we do. Yeah, yeah. And it's a good class, and we'll look at retroreflectors, and we'll look at all these. Uh, we can do this with our sensor, and we can do this with our sensor, but we can't do this. So we can't do what we call through the beam. So these guys right here will start off false, and they'll be true when they see something. This retroreflector, this guy will be true if it don't see anything, and then when you break the beam, it'll become false. So that's something you have to realize when you. So one of the things they do in that class is we do this, and they'll use like a normally open contact, and it'll start off energized when we want it to start off de-energized, right? So they have to figure that out. So that's something that you'll see in a sensor. So these guys, they'll be true when they don't see something. Their outputs will be true if you're using a normally open contact, and then when the object breaks it, that's when they become false. And that's the same thing through with what we call a through the beam. So here's my object I'm trying to detect, so the light will be going through. So if there's not an object, then these guys here will start off true, and then when the object comes in and breaks the beam, so the object really breaks the beam, and so the output would become false. The advantage of a through the beam over retroreflective is you have a large, but here you have a separate receiver and a separate sender or transmitter. Over here for the diffused and for the retroreflective, you have one transmitter and one receiver that's in one unit. So that would be the advantage there. The advantage of a through the beam. So this guy here has got to go all the way to the retroreflector and bounce back. So that means if you use the same light intensity and you had the same receiver, then the through the beam could detect, we could have them spread further apart. We had this, they had the line crew at U.S. Steel had their wire yard. That's where they kept all their spools of wire and stuff. What happened is the guy was working some shift, and they had that big old spool of wire, and he come over here and he started spooling it off and ran it through the chain link fence. And then he came back at night and hooked a rope to it, to his car, and pulled that whole spool out down 10 Mill Road, which is blocked off now, and rolled it over on the side. And he was coming out there cutting links off of it, and he was going selling it. So, and they finally figured it out. I don't know if they caught the guy or not, but they finally found the wire. And I don't remember that story. And so what we did is we put a through the beam detector, and these suckers, them things must have been, good gracious, 100 feet apart. And we set it down. Originally, we put it pretty close to the ground, but the rats and everything would set it off. So we moved it up probably around, probably a foot off the ground, and those things worked great. And then they came in and put a real small gauge wire down the chain link fence that you couldn't even see, and if somebody would cut it to get in there, it would break the wire. So that's the two things that we added. But that was a through the beam, and those things were at least 100 feet apart. And they used infrared, so you couldn't see the beam. You couldn't see if you didn't know they were there. You wouldn't know it. So that's the big advantage of a through the beam, is it's got twice the range of a diffused, or a retroreflective. Diffuse is going to depend on the color. So the darker the color, the less light it's going to reflect back, and the brighter the color, the more light it's going to reflect back. So we could use a diffuse basically to sense not the color, but what we call shades of gray if we wanted to. So that's one thing that we can do there. So we have diffuse sensors on the Amatro line. Like I said, it's on the entry end, but it won't see black. So if you drop those that's got that RFID tag on there, then if you put the tag down, it'll say there's nothing in there. It says there's nothing in the magazine. So these guys are very reliable, but they're electronic, so they're either going to be 3-wire sensors or they're going to be 4-wire sensors. And we'll talk about that in a minute. And I'll give you all the color code, which is very, very important. So we have a standard color code that's out there too, that we can see what the power leads are. In fact, let's go. So plus DC is going to be brown. Minus DC is going to be blue. Brown, I think, is 1. Minus is pin 3 on the pin numbers. And then the signal wire is going to be black. And it's going to be on pin 4. Black is going to be a normally open. And then if we're 4 wires, what they have inside this is I'm drawing it as a switch, but it's actually solid state. What it's going to be is it's going to be a double pole, double throw. So what we do, we have a common, and then we'll add a wire on 2, and it's going to be white. And this is going to be the normally closed, if we have a normally closed. So a lot of times they won't use the black wire, they'll use the white wire. Sometimes most of ours don't have a white wire. Most of ours will just be brown, blue, and black. So that's the color code, and that's the standard color code for these solid state sensors. So now it makes it, because the problem is the wires are not numbered. If you a lot of them have a screw in, so a lot of them are set up to be repaired. So they'll have a little plug that screws on that connects the 3 or the 4 wires. Some of them some of the sensors, the wires actually go into the sensor, which means you would have to you'd probably have a terminal board out there, but you would have to pull the wire all the way out to the terminal board. So those are those are cheaper, but you know, if you're using wire ties or something like that, you'd have to cut them off and put them back in there. But most of them would run through like a plastic cable trough. So through the beam, so these are examples of through the beams. We have one of those on the Amatro line. We have one. We probably have about 3 or 4 of them on the Festo line. Well, we have more than that. A diffuse sensor, we have one of those on the Amatro line. We have several on the Festo line. And through the beam and diffused. Retroreflective. I know we have 2 on the Amatro line. And we've got several, 2 of them right off the bat I know on the Festo line. So both these lines have all 3 of these types of photoelectric sensors, but non-contact. Remember, the diffuse sensor starts off false, so its output is false unless you see something. The through the beam and the retroreflective, those sensors start off true. And then when the object breaks the beam, it becomes false. And if you're a PLC programmer, you definitely need to do that. Or if you're like I said, somebody's going to do this in sensors. We're going to use a diffuse sensor, and and they're going to use normally open contact when they should use a normally closed contact. So this is retroreflective. So ours actually has this reflector, but they have different types of retroreflectors. They have beads. This is usually what the street. That was me. I thought somebody. Okay, this is usually what the street department usually uses beads. They're glass beads that they'll have wet paint out there, and you'll see them throw those glass beads. And sometimes I've been through there where you can actually see where they before they come back and sweep them up. Of course we have retroreflective tape. You can buy, these vests that people that work around the street. Those are retroreflective, which means it reflects back to the car, even though the car is not pointing directly at the person. It reflects back to you because those are retroreflective tapes too that we can get. This is diffused. We've already looked at this. These are what we call, these are through the beam, but they're set. The transmitter and receiver are set. And so what we have is we have a transmitter on one side. They'll usually label it D. And then we'll have a receiver on the other side. I'll have to look, guys. And then and it's usually infrared, which means you can't see it. But we've got, and the Amatro line has several of these, and we'll see what they use on that. I can't right off the bat think of any of these that's on the Festo line. This is usually what they use in your printer that senses when it gets over to the left. So what happens is the blade is precise, and we come over here and we move a device through the blades, and then it senses them. So these would start off true, and then it would turn false. This is basically what it's made of. It's made of a light-emitting diode, and like I said, most of them are infrared, which means it's there, but you can't see it. And then this runs into a phototransistor. And what this does is this replaces that lead that controls the size of the valve, which we call the base. So, by the way, on these transistors, it's got an arrow. And so we got two symbols. After this, we'll break, guys. So we got this guy right here. And then we got this guy right here. Now notice one of them, the arrow's pointing in, and the other one, the arrow is pointing out. So this guy right here is not pointing in. So that's the symbol of an NPN transistor, and this guy here is we can't use. These guys is pointing in, so this is a PNP. So this guy right here would be used in syncing. This guy over here would be used as sourcing. But these are current valves. So what we do is on this base lead, we put a very little current that controls a lot of current flowing through here. And the amount of current we put into the base controls the size of the valve. Well, what here is we're actually using a photoelectric device right here that's replacing the base. So these phototransistors, these are called phototransistors. The actual size of the size of the valve, how much the valve is open or closed, will be determined by the amount of light. So they put enough light through here that causes this thing to turn wide open. We refer to it as saturation. So the output would be 0 because it's bringing common up to here. And then when the light goes away, it turns off. And now the output will go up to plus 5 volts because there's no current flow through that resistor anymore. So these are photoelectric. These are these optical interrupters. But they're nothing but through the beam. But the transmitter and receiver is in one unit. And we'll show you all these on the Amatro line. So we have a gantry crane that sorts the valves, and the position that lines up with the magazines is going to be set by these optical interrupters. So we show those. I don't think we got any on the Festo line. I'd have to think about it. And here's one. I'll let y'all hold one of these. One of them's called E, emitter, and one of them's called, oh golly, I should know that, detector. I think one of them's E and one of them's D. And then it'll have, they're DC, so it'll have a plus sign up here, which tells you you need to put the plus DC on this one, and then the minus would go to that side. And so what we'll do is we'll come up here and we'll look at these. So we got several things that we want to do, and we'll try to find these. And we have a sheet, and whether you find them all or not, it's just something that you're going to try to do on your own and see if you can figure out what these things look like and what they are. The Festo line, the optical sensors, the photoelectric sensors are pretty obvious because they have fiber optic cables. In fact, the Festo uses plastic fiber to bring it up from the input. The Amatrol line. The inductive sensors should take metal. The capacitive sensors, you should be able to take your finger and touch them. By the way, most of your solid state sensors will have a amber LED on them that light up when they're true. But you can also look at the PLC and see when a light comes on or goes off, and I'll show you all that too. And so that's the one thing good about a programmable logic controller. It's got those light emitting diodes on on the inputs. So if the input's true, the light comes on the PLC. So you can actually trigger these sensors with whatever they see, and you're checking the wiring all the way to the PLC. So if you trigger the sensor and the light comes on the PLC for that input, then you know all the wiring. Not only is the sensor good, but all the wiring between the PLC and the sensor is good, which is pretty neat. We used to ohm them out with meters and all that other kind of stuff. So programmable controllers are really good. They help you. They make troubleshooting a lot easier. So guys, that's all we're going to do tonight. Y'all got any questions? I know we went over a lot of stuff. So when we come in, we'll look at capacitive sensors on Wednesday. I'm sorry. We're coming in on Monday, right? So when we come in on Monday, if I say Tuesday, guys, y'all got to just remember I'm turning 70 years old. So y'all just remember that. So we come in on Monday. We'll talk about capacitive sensors. We'll look at inductive sensors, ultrasonic sensors. Pressure sensors. There's no pressure sensors on the Festo line, but there is on the Amatrol line. We'll look at radio frequency ID or RFID tags, which are very popular. Y'all run into these all the time. Most grocery stores have them. Well, not grocery stores. Most stores like Walmart has them now. Temperature. We don't have any temperature sensors, but we need to talk about these. And then we'll look we'll talk a little bit about PLCs. So any questions? So what are we going to do Monday? Some of y'all haven't done y'all syllabus quiz. Some of y'all did the syllabus quiz, and you did the syllabus quiz, and you did the syllabus agreement, but you didn't do those other agreements. So you didn't make 100 on. So I'm going to give y'all an extension on assignment 1. So if you hadn't done your syllabus quiz, you need to go. By the way, once I put a 0 in there, and you go and take that test, it's not going to update because I override that so you can see what your grade actually is. So that means this, just because you go out and take the syllabus quiz and you go back in there and it still shows you got a 0, it don't mean you got a 0 on it. It just means I haven't went in there and removed the override. So that's what we have to do to get a feel of the grade. If it don't have a grade in there, then it's not included in the calculation of your grade. So that means if you took one test and I didn't enter the grades for test 1, 2, 3, and I didn't enter the grades for the final or anything else, it would show you had an A in the class. But if I override it, then it's not going to show up when you go up there and complete it. I have to get around and come back and check that. So that might be one reason to send me an email, saying I went and completed that. So y'all need to do that. So some of y'all that hadn't, or if you completed the quizzes, but you didn't make a good grade, then of course you got 100 on assignment 1, but you might not have a real high grade on first week quizzes and assignments. So you can take until this I think until I need to put that deadline until you can't do these all semester long because they're first week quizzes. But I'll give you until next weekend to go back and try to get the highest grade on your syllabus or whatever. Of course, your agreement you should have got 100, but your syllabus quiz and your safety and evacuation quiz, you can go back and try to retake those and get the highest grade that y'all can get on them. Y'all can take them those an unlimited number of times. So I'm giving y'all that opportunity, and then after next weekend, let's do Friday. So after Friday, I'm gonna make them invisible, and you won't be able to go back and retake them to increase your grade on first week quizzes. All right, guys, y'all be safe, and I'll see y'all on Monday on campus. Okay, Monday on campus. All right, y'all be safe. Yeah. By the way. Yeah, if you got any questions, I'm hanging around. Let me pause the lecture.